motions, and we will learn how to solve problems using free body diagrams, how to sum forces, and work with vectors, and also create equations of motions. And to make it clear, we're going to go through an example for each of Newton's three laws. But before that, let's take a quick review on the three laws of motion of Newton, well, the ones that Newton made or stated. Anyway, the first law is the law of inertia, which states that an object at rest stays at rest, and an object in motion continues to move at a constant velocity unless acted upon by an external unbalanced force. This is written as sigma F equals 0, which just states that the sum of all forces acting on an object in a system is equal to 0, so it experiences no force, so it doesn't move. The second law states that the net force acting on an object is proportional to the product of its mass and acceleration. This is written as sigma F equals ma, where the sum of all forces in a system acting on an object is equal to the mass multiplied by the acceleration. And the third law states that for every action, there's an equal and opposite reaction. And this is written as the force that object 1 exerts on object 2 is equal to negative force that object 2 exerts on 1. And I'll state what this negative means later on. So let's just get right into the first problem. So the first problem involves the law of inertia, Newton's first law, right here. So the problem says a 10 kilogram ball is at rest on a table. So A, we need to calculate the magnitude of the force of gravity acting on a ball. So first of all, we will draw a free body diagram of the ball. So we know that it's a ball, obviously, so we're going to draw a circle. And we know that it is at rest on a table, so it's not moving, it's not accelerating. So because of that, we're going to remember all the forces come from the center of the object. We know that the force of gravity is acting on the object and it's pointing down towards the ground. So there's the force of gravity, and we'll label that F subscript G, and we're going to add the vector arrow. And basically, remember, a vector is just any quantity that has size and direction. So mass, like the 10 kilogram ball, the mass is a scalar quantity, it only has size, but the force of gravity also has direction, which is why we write this vector sign. And you need to take into account the direction when performing calculations, but we are going to do that. I'm just going to show you how to do that real quick. Anyway, first let's finish the free body diagram. And we also know, remember from the previous episodes, there's a normal force also acting on this object, and that repels the force of gravity. And remember, it's also a vector. Alright, so here you can see the arrows are roughly equal because the two forces should be equal in magnitude. Anyway, now let's write out an equation of motion. An equation of motion simply takes the drawing of the free body diagram and puts it into a mathematical equation. So first of all, we know, let's just write out. So sigma, remember, sigma just means sum of all forces. Oh, almost forgot to label the free body diagram. Remember to always label a free body diagram. Otherwise, your teacher or whoever is grading your paper or test might take off points. And we're going to write ball. Alright, anyway. So the sum of all forces, remember to write a vector sign, is equal to 0 because it is not moving. Remember, the problem said it's at rest on a table. So we know that in the y direction, which is up or down, it's not moving because the force of gravity is pulling the ball downward, but it's cancelled out by the normal force. And we also know it's not moving left or right because, well, it's at rest, so there's no forces acting on it. So we'll just quickly label that here. We'll say balanced forces because this is gonna, well, when I was in school, this is what we did, so. And apologies for the handwriting, it's hard to write with a mouse. Alright, now let's expand this equation of motion. So remember when I said vector, right? Now, to take into account the direction of this, first we need the direction of the vectors to make a right calculation. We need to know exactly what the direction that's going to be positive is. So, let's just say the positive direction is going to be up. So we'll just state that, right? So now we'll expand this. So Fn is up, the normal force is up, so we're just going to take the vector off, now it's only magnitude, and we're going to write a positive sign right here. You don't need to write this because it's already implied, but I like to write it to remind me of what I'm doing. And then the force of gravity is pointing downwards, and since we know that up is positive, then downwards is going to be negative. So we're going to write negative Fg. And this is going to be 0. Oh, whoops. We skipped a step. First, we were supposed to calculate the magnitude of the force of gravity. Well, let's just expand that over here. So we know that the force of gravity is just equal to the mass of the object multiplied by the acceleration due to gravity. So this is just going to expand to 10 kilograms times 9.81 meters per second squared. And this calculates to 98.1 newtons. However, keep in mind significant digits. So here there's 2 and here there's 3. We always go with the one that has less, so we need to round to 98 newtons. Otherwise your teacher may take off points. Anyway, back here. So we can expand, well, we want to figure out the magnitude of the normal force. So we can just say Fn is equal to Fg. Simple manipulation, we just add Fg to both sides. So Fg over here is going to cancel, and Fg is going to be added over here. And if we know that Fg is 98 newtons, then we can simply say that the normal force acting on this object is also 98 newtons. Anyway, that was a very simple example. Now we're going to go on to Newton's second law. So in this question, it states that a 10 kilogram ball is pushed across the table with a force of 10 newtons. Calculate the magnitude of the acceleration acting on the ball. First of all, we need to draw the free body diagram. So remember, label it FBD ball, and then we will draw it. So here, oh, also in this scenario, ignore friction. We will talk about friction later on. Alright, so first, the force of gravity. Remember, it's a vector. And then the normal force, which is also a vector. And then it says that it was pushed across the table with a force of 10 newtons. Now, it doesn't matter if it was pushed left or right, but for simplicity's sake, I'm just going to say it was pushed right. And we'll say F-A. And what this means is it's an applied force, which literally just means the ball had a force applied on it, and that force was 10 newtons. Alright, that's just what an applied force is. In later episodes, we'll elaborate on like strings and tension and how they're also applied forces. Anyway, for now let's write the equation of motion. Now, as you can see in this free body diagram, there's two axes. There's the y-axis with the normal force and the force of gravity, and there's the x-axis with the applied force. Now, since we only need to calculate the magnitude of acceleration acting on the ball, and we know that the ball is not moving up and down, it's only moving, well, to the right, that means we only need to focus on the applied force. So, remember, first we're going to write the sum of all forces in the x direction, so we'll just write x here is equal to mass times acceleration. And remember, the positive axis because vectors need to take into account direction, is going to be right. So we'll just put an arrow pointing right there. Now we'll just write FA, and remember positive is equal to positive A, and acceleration is positive because the acceleration is always in the direction of the net force acting on the object. So here the net force is clearly seen acting to the right, therefore the acceleration is also going to be positive. And here we know that the force is 10 newtons, correct? So we are, oh wait, sorry, I'm skipping a step. So now we can drop the positive because that's implied. Now we just want to rearrange the equation for the acceleration. So we're just going to divide both sides by m, by the mass. So here we get that acceleration is equal to FA over m. And now we can substitute the numbers in. Remember to always write the units as well. Whoops, not 10 kilograms, 10 newtons over the mass was 10 kilograms? Yes. Alright. Now if you did dimensional analysis on the units, you would see that the kilograms here cancels out with the kilograms that make up a newton, and you're left with meters per second squared, which are the units for acceleration. And remember to take into account the significant digits. So when we plug this into our calculator, we get 1.0 meters per second squared. So this means that this 10 kilogram ball was pushed across a table with a speed, or with an acceleration of 1 meter per second, meaning it started at 0 meters per second at rest, and then someone pushed it, and it kept gaining 1 meter per second of speed for every second that passed. So after 2 seconds, the ball was at 2 meters per second, and after 3 seconds, it was at 3 meters per second. Anyway, that was the most complicated problem today. Again, in the 5th and 6th and so on, we're going to make the problems way harder. Now we'll move on to the final one, which is using the third law. Now this one is mainly just logic. So it says that a person pushes against a wall with a force of 50 newtons, and we need to calculate the magnitude of the force exerted on the person. Remember, Newton's third law states that for every action there's an equal and opposite reaction, and this is written as F1 on 2 equals negative F2 on 1. Well, now I'm going to elaborate on the negative. So here, let's just write F1 on 1 on 2 is equal to negative F2 on 1. Now, as you can see, I wrote a vector sign for F1 on 2 because we don't know the direction the person pushes against the wall. He could be pushing a wall to the right, or he could be pushing a wall to the left. But we do know that since the person, whatever direction the person pushes the wall in, the force that's exerted back onto the person is going to be in the exact opposite direction. So it has to be negative. And negative is how we take into account the opposite. So if we know that let's just say he was pushing to the right, then we'll say positive 50 newtons is the force applied on positive 50 newtons is the force the person applies on the wall. Well, oh wait, whoops, hold on. I think I could have done a better explanation here. Forget about the negative sign over there. Alright, we'll just erase this. You can actually rewrite F2 on 1 as being negative F1 on 2. So whatever value this is, just make it negative. So that means the force was negative 50 newtons to the left if the person was pushing right. This is the force exerted onto the person by the wall. But remember, the question said magnitude, so drop the negative sign and just say 50 newtons. And also remember, this is why the you just don't go through a wall, right? If you punch a wall, well, if you punch the wall hard enough, then it breaks. But let's just say you punch a wall and it wasn't enough to break the wall. The reason your hand didn't just phase through is because the wall exerted a force back onto you. And let's say you do punch a wall, a brick wall, then the reason it hurts is because the force was exerted back onto you. Anyway, that was everything for today. We will expand more on our free body diagrams and equations of motions, but these were just a very basic introduction to them. Anyway, thank you for listening, and that is everything for today.